Hi guys, I hope that you are having a good weekend or week depending on when you're watching this video. So last week I posted a lot of videos. Everything I've posted up to this point has been done via screencast, which is where I film my computer screen and then I kind of lecture in the background. And I know that people have different preferences for how they learn and learning styles, particularly when it comes to mathematics. So this week I'm going to mix it up a little bit and I'm going to do more of a traditional lecture style video. I'm going to review some of the basics that we've covered thus far to kind of help maybe connect some dots that haven't connected yet for some of you. And then I'm going to introduce our new topics this week, which is expanding upon the concept of doing inferential statistics with proportions. So the first thing I wanted to review is this concept of probability distributions. So we've talked some about probability in this class. I haven't gone super in-depth in it as much as we probably could because I think it's more important that you guys get applicable skills out of this class and less focus on the theoretical understanding behind it. But essentially what we do in statistics is we want to be able to conduct an experiment on a small group of people, which we call a sample, and we want to be able to try to generalize those findings to a larger group of people. And the way that we do that is based on probability. So we look at the results of our sample, provided that it's gathered under the right circumstances, and then we're able to estimate the probability of seeing that result if our null hypothesis was incorrect. So we won't get too heavy into that quite yet, but the main thing I want to talk about first is this concept of probability and probability distributions. So in this class, we've talked about rolling a dice, and what happens when you roll a dice, if we are going to try to draw what that looks like, is it's essentially one of those uniform distributions, except that each possible outcome has an equal equivalency, but there's no space in between. So what does that mean? That means this is the probability of rolling a 1, probability of rolling a 2, 3, 4, 5, 6, and so on. They all have an equal probability because with a little dice, with dice, there's 6 sides. It's not weighted, so there isn't going to be an unfair advantage for rolling a 1 versus others, so it has an equal probability. Another concept we talked about was uniform distributions, which are just another way of visualizing what a probability could look like. The difference with that one is it would be a continuous x-axis, meaning that you could roll a 1, 2, 3, 4, 5, 6, but you also could roll like a 1.5 or a 5.453 or something like that. So uniform is representative of a continuous variable along the x-axis, whereas our visualization of rolling a dice would be a discrete variable because there's only 6 discrete outcomes and there's no possibility of rolling a dice and getting like a 1.5. So in statistics, we talk about probability distributions because it basically allows us to visualize the probability of something happening. And one of the most common ones used, which I talked about I think about 2 weeks ago, is called the normal distribution, or as some of you maybe have heard it called, it's a bell curve. So the characteristics that are important about the normal distribution is the center of the data, of the distribution, which is the mean. In a standard normal distribution, the mean will always be 0. The other important thing is the standard deviation, or because we know the standard deviation, which is always 1. So what that means is if I move 1 standard deviation here, that value is 1. 2, 1 standard deviation down from 0 would be -1, -2. So what is a probability distribution and what exactly does this mean? So how you should look at this distribution is there's other important things to note. So we've talked about the mean being the center of the distribution. We've talked about the standard deviation, which is just the average space between the data points and their mean. But the other important things to note are the y-axis and the x-axis. So the y-axis is what we call the frequency with which a value occurs. So what that means is when we look at our data set, underneath this curve, a lot of times we just draw this line and we expect you to understand what that curve means. But what happens under this curve is there's actually lots and lots and lots and lots and lots of data points. This whole thing is filled with data points. So what happens is the x-axis is telling us exactly which data point or value we are looking at. So if we said how many of the data points in this distribution are 0, we would look at our 0 on our x-axis and we would try to measure how tall that curve is. So what happens is with a normal distribution, the center of the data, the mean, should be the place with the most frequently occurring points. So I'll say that again. The mean is going to be the most frequently occurring value in this distribution. But what happens is as we move away from the mean, those values don't occur as frequently. This is why we often use means in statistics to be representative of a group. So if I asked you what your grade point average is, that's essentially a calculation of a mean based upon the grades you typically earn. We use the mean as a representative of what your overall grade point average is. So even though you might maybe get a really high grade in one class and a really low grade in another class, we look more at the average and not specifically at all the individual grades that you earn. So the thing that's really interesting about the standard normal distribution is that yes, the mean is important. It is the most frequently occurring point, but if you look, it's not the only occurring value, right? So we have values that are not equal to 0. So we have values moving all the way out to 1, 2, and even further. What that means though, is that if I'm going to randomly select a data point from this distribution, this data point has a very high probability of being close to the mean. So it's probably going to be approximately, this is my data point, approximately equal to the mean. There's going to be a much higher probability of pulling these data points because they're the most frequently occurring. However, I could pull a data point and it could be really far away from the mean. I could pull a really crazy data point out here of 3.14. So while it is possible to pull that data point, because the values over here are way less frequent, the likelihood of me pulling that value point is rare. It's much more likely that I'm going to pull a data point somewhere from the middle of the distribution. So the reason that the standard normal distribution is important and the reason that it is used in statistics so often is that because we understand the shape of it and the frequency with which these values occur, it allows us to calculate probabilities. So if we do calculate a data point somewhere in this distribution, we're actually able to calculate the probability of obtaining that data point, which gives us a good starting point to say whether or not it seems like there is a significant difference between two groups, or basically calculate the likelihood of obtaining that point, and then we kind of compare that to our experiment. So there's really fancy mathematical ways of calculating the probability of these points, but I'm going to give you kind of a simple version and I'm going to tell you the easy way for you to find those values. So what the probability is it's actually the area under the curve. So the entire area under this curve, and the reason that we draw this line when we talk about bell shapes, is that all of the probabilities of pulling these data points is equal to 1, which should seem really familiar because we talked about that in our unit on probability. Because we know that all of the area under this curve is equal to 1, we're actually able to calculate the probability of pulling a point equal to or greater than 2 by finding the area located at that value and out. So what that means is if I wanted to know the probability of pulling, these are z-scores, of pulling a z-score greater than or equal to, remember greater than, the big mouth opens towards the bigger number, greater than or equal to 2, I would calculate the area from the 2 out through the tail because every value out here is greater than 2. So there is a way to calculate that, but that's outside of the scope of this class. So what I would like you to do, if you have it available, is open your book and turn back to Appendix F. So what Appendix F is it actually is the z distribution, right? The standard normal distribution, and it gives you the probability of obtaining all these different z-scores. So the way that you look at it is if we were going to look for 2, we would keep in mind that it's not just 2, right? It's z equal to 2.00. So what you would do is you would look in the very first column, you'd move down until you find the place where you see a 2. There's a 2.0, a 2.1. We're looking for the 2.00. So we would say 2.0, and then the column right next to that is 2.00. I'm gonna step a little closer. Hopefully you guys can see. 2.0, this is the 0 column, and then we can find the number right here. I'm gonna read it upside down. Hopefully I'm not dyslexic. 0.04550. So that's the probability of obtaining a z-score equal to 2 or greater.